What's going on, everybody? Got another video here for you. This one is Lagrange Multipliers, so let's get into it. Alright, so method of Lagrange Multipliers. It says to find the maximum and minimum values of f of x, y, z subject to the constraint g of x, y, z is equal to k, assuming that these extreme values exist and del g does not equal 0, which, if you remember, this is the gradient vector, does not equal 0. On the surface, g of x, y, z equals k. All right, so 1, it says find all values of x, y, z, and lambda such that the gradient of f equals lambda times the gradient of g, and g of x, y, z equals k. So we're going to have a system of equations to solve. All right, then it says evaluate f at all points x, y, z that result from step 1. The largest of these values is the maximum value of f, and the smallest is the minimum value of f. So this is finding maximum and minimum subject to some kind of constraint. So let me just move this over out of the way over here so I can have some room. I'm gonna kind of sketch this out for you. So if we have this, all right, and you have some curve here, okay, some curve like this, and this is your curve g of x, y, z equals k. All right, and so you have these. You can have these level curves coming in here. This would be, say, f of x, y, z. Nah, not f of x, y, z. F of x, y. And I don't know why I put a z there. That's g of x, y equals k. So let's say this one equals 7, and then we have another one here. This would be f of x, y equals 8, and then have another one here. F of x, y equals 9, and then have another one here. Say f of x, y equals 10, and then you have one here, f of x, y equals 11. And this is what you're doing. You're looking subject to the constraint that it falls on this g here, and this right here, you can see this point right here, that would be your maximum. We have a value of 10 there. Okay, we wouldn't look at this one because it's not on this curve g here. All right, so that's basically what we're doing. So, after going over this, we've got the gradient of f is equal to lambda times the gradient of g, and g of x, y, z is equal to k. So we're going to solve that system of equations and then evaluate the function at those values. So what we can do, if we write the vector equation gradient f equals lambda gradient g in terms of components, then the equations in step 1 become the partial of f is equal to lambda times partial g, and that's with respect to x. And then we can write the partial of f with respect to y equals the lambda of g, the lambda of partial of g with respect to y. And then we can do with respect to z, and then we have our constraint here, the g of x, y, z equals k. This is a system of 4 equations and the 4 unknowns, x, y, z, and lambda, and we must find all possible solutions. And then we have for functions of 2 variables, you can see it's similar. We don't have a z component here, but you're going to do it basically the same way, except when you do the partials, you'll just go partial with respect to x, partial with respect to y. All right, so let's look at some examples. Let's jump into some examples and see what we can find here. So it says find the extreme values of the function f of xy is equal to x squared plus 2y squared on the circle x squared plus y squared equals 1. All right, so let's work this. So we have the gradient of f is equal to lambda times the gradient of g. And so we've got the partial with respect to x is equal to lambda times the partial of g with respect to x. And then we've got the partial of f with respect to y equals lambda times the partial of g with respect to y. And then we have g of xy is equal to 1. All right, so let's see what we have here. All right, so we have 2x is equal to 2x times lambda. All right, now all I did, see, partial of f with respect to x, that's the partial of this with respect to x, that's 2x. This is a constant, that's a derivative, that is 0. And then we have the partial of g with respect to x, so that would be 2x. The derivative, that would be 0. Okay. All right, and then of course times the lambda. And then we have the partial of f with respect to y, so that's this one, that's going to be 4y is equal to 2y times lambda. And then we have g of xy equals 1, so that's x squared plus y squared equals 1. So we have our equations here that we need to solve. So let's take this one. So that's going to give us 2x, right? 2x minus 2x lambda equals 0. So 2x times 1 minus lambda equals 0. So you can see x equals 0, and we have lambda equals 1. Okay. All right. So we can see that if x is equal to 0, then that's going to give us 0 squared equal, that's going to give us 0 squared plus y squared equals 1. So this is going to tell us that y squared is equal to plus or minus 1. All right. So what I did there is, see, I got x equals 0 here. So I took the 0, plugged it into this one, and solved for y. And then we can see if lambda equals 1, well, you can see here that gives me 4y minus 2y equals 0, right? And so 2y equals 0, so y equals 0. So if y is 0, that's going to give me x squared plus 0 squared equals 1, so x equals plus or minus 1. All right, so I took the 0 that y equals 0, I plugged it into here and solved for x. And so now I have the points 0, 1, okay, 0, 1, 0, negative 1. See, x is 0, y is plus or minus 1. I don't know why I have a y squared there, but y is plus or minus 1. And then for this one, y is 0, x is 1, and negative 1. So that's going to give me the point 1, 0, and negative 1, 0. And so what does it say to do after I get all my points? I take the points and I plug them back into here. All right. So that's going to give me f of 0, 1 is equal to, so when I plug that in, that gives me 2. F of 0, negative 1 is also equal to 2. F of 1, 0, so I'm going to take this point and plug it into f. That's going to give me 1, and f of negative 1, 0 is also going to give me 1. So you can see that f of 0 plus or minus 1, see, these are my two largest values here. So those are my maximum. So that is a maximum value, and then f of, let's see, plus or minus 1, 0. See, these are giving me my smallest values. That is a minimum value. And so there's your answer right there. So you can see that's not too bad at all. All right, it's not too bad. And I would say probably what's going to be the most difficult part of these problems is solving the system of equations. You'll have you might have a few little tricks you need to do and stuff like this. All right, so let's look at this example. This is an example that we worked in the last video when we did maximum and minimum values. Well, we're going to rework this problem, and we're going to use Lagrange multipliers to do it. So it says a rectangular box without a lid is to be made from 12 square meters of cardboard. Find the maximum volume of such a box. All right, so you've got your box here, right? Here's your rectangular box. All right, and we know the volume is x times y times z, right? All right, so that's the volume. And then we've got g of x, y, z, okay? So we have our constraint here that it's made from 12 square meters of cardboard. So, we looked at this in the last video, how we came up with this. So if you take the area of this side and the area of this side, that's xz is that area. So xz plus xz is equal to 2xz plus, and then we can look at this front side, and we can look at the back here. That is y times z, so you've got two of those, so that's going to be plus 2yz, and then you've got the area of the bottom here, so plus xy. Now remember, we're not going to add the top in because it says without a lid, and we know that is equal to 12. All right, so we've got the gradient of v is lambda gradient of g. All right, so let's see what we've got here. All right, so that's going to give us Vx is equal to lambda times Gx Vy. And when I say Vy, I mean the partial of V with respect to Y. And that's going to be Gy, and then Vz is lambda Gz, and then we have g of x, y, z is equal to 12. All right, so let's go ahead and take these partials. So let's do this one. The partial of v with respect to x is going to be yz equals lambda times, and now we do the partial of g with respect to x. So that's going to be what? 2z plus y. Plus y. Whoop. All right, and then this one we've got xz is equal to lambda times, and then the partial of g with respect to y. That term's going to go to 0. That's going to be 2z plus x. And then we have, what is that? That's partial of v with respect to z. That's going to be xy equals lambda. And then that's going to be 2x plus 2y. And then we have g of x, which is 2xz plus 2yz plus xy equals 12. So here's our system of equations we need to solve. All right. So when we look at this, you know, we're sitting there thinking, well, how in the world can we solve this? Well, if we multiply this first equation by x, multiply the second equation by y, and multiply the third equation by z. So what am I doing there? Well, I'm multiplying this one by x, this one by y, and this one by z. And the reason I'm doing that is because it'll give me x, y, z here. X, y, z, x, y, z. And so I'll have x, y, z equals each one of those things. And then that's going to allow me to set the right-hand sides equal to each other. Okay? Set the right-hand sides equal to each other. And then I can solve. And so this is going to give me x, y, z equals, let's do it, lambda times 2xz plus xy, right? Multiply everything by x. And then I got x, y, z equals, multiply everything by y. That's going to be lambda times 2yz plus xy. And then I've got x, y, z equals lambda times, let's see, what is that? 2xz plus 2yz. And then, and I also have, don't forget, we have our g of x equals 12. All right. All right, so let's see what we can do here. So you notice on the left-hand side, I've got x, y, z equals. Okay. Now, when we look at this, lambda could be 0. Okay. But that would mean yz equals xz equals xy equals 0. Okay. So lambda cannot equal 0 because if x, y, or z is 0, then that would not be the side of a box. Okay. So we know lambda can't be 0. So let's take this one and set them equal to each other. Okay. So let's take let's see, where is it? 2xz plus xy equals 2yz plus xy. All right. All right. So doing that is going to give us what? That's going to tell us that 2xz is equal to 2yz, which that's going to mean that that's going to mean that x equals y. I can divide both sides by 2, and I can divide both sides by z. I can divide both sides by z because we know z can't be 0, so I wouldn't be dividing by 0. Okay, so I've got x equals y. All right, so now let's take the 2yz plus xy and set that equal to 2xz plus 2yz. All right, so I've got 2yz plus xy is equal to 2xz plus 2yz. All right. Now, I don't know if you might be asking this. You might be saying, well, why aren't you bringing the lambda down? Well, if I did bring the lambdas down, I could divide both sides by lambda, and they would just cancel out. Okay. All right. So what do we have here? Well, notice the 2yz, the 2yz, those cancel out. So this tells me that xy is equal to 2xz. And so this tells me y is equal to 2z. So y is equal to 2z. And we can divide by x because we know it's not going to be 0. Okay. All right. So what I'm going to do now is I'm going to take my equation 2xz plus 2yz plus xy equals 12. So I'm taking this, my g of x, g of xy, g of xyz equals 12. I'm going to take that and I'm going to plug the 2z in for x and y. And then that way I'll be able to solve for z. So I'm going to plug the 2z in for x and the 2z in for y. I can plug 2z in for x because I know y is equal to x. And so that's going to be 2 times 2z times z plus 2 times 2z times z plus 2z times 2z equals 12. And basically when you do all of this right here, that's going to give you 12z squared equals 12, which that tells us z is equal to plus or minus, well, z is equal to 1. It's plus or minus 1, but we know z can't be a negative. And so z is 1. We get y is equal to 2 times 1, which is 2. So we also know x is 2. So our maximum volume is 2 times 2 times 1, which is 4 cubic meters. And there's your answer. All right. So, it's the same problem we worked in the last video on maximum and minimum values. We're just using a different method to solve it. Okay. And you can see it's not too bad. All right. I left myself plenty of room to work on this section. All right. Find the points on the sphere x squared plus y squared plus z squared equals 4 that are closest to and farthest from the point 3, 1, negative 1. All right. So we're wanting the closest and nearest of the distance, right? Distance. So we've got the distance formula. So we have a point, 3, 1, negative 1, and then we want a point on the sphere. So that would just be some point x, y, z, right? So if I do the distance, remember the distance formula, x minus 3 squared plus y minus 1 squared plus z plus 1 squared, and it's the square root of all that. All right. And then if you remember from the last section, we did a problem similar to this in the last section, that we can minimize the square, the distance squared. That's our f of x, y, z, which is equal to x minus 3 squared plus y minus 1 squared plus z plus 1 squared. Okay. So this is our f of x, y, our f of x, y, z, and we have g of x, y, z is equal to x squared plus y squared plus z squared, which equals 4. All right. So let's see what we have here. So remember, we have gradient of f is equal to lambda times gradient g. And that's going to give us the partial of f with respect to x equals lambda times partial of g with respect to x. And then we've got the rest of them here, lambda gy. Z is lambda gz. And then we have g of x, y, z equals 4. Okay, so this is what we're doing here. All right, so now let's do our partials. So if I do the partial of f with respect to x, this term and this term go to 0. They don't have an x value. And this is just chain rule. So I've got 2 times x minus 3 is equal to lambda times, we can put lambda times 2x, or you can put 2x lambda, it doesn't matter. And then the partial of f with respect to y, that's 0, that's 0. We do the chain rule on that. That's 2y. That's 2 times y minus 1 equals lambda times 2y. And then 2 times z plus 1 equals lambda times 2z. All right. And then we also have our constraint x squared plus y squared plus z squared equals 4. All right. So now let's take each of these. Let's solve this for x, solve this for y, and solve this for z. So what I'm going to do real quick is I'm going to go through and solve this one for x and show you how to do that. You should be able to do it. 2 times x minus 3 equals lambda times 2x. I'm just going to go through all the steps, show you solving it for x, and then the other ones will be similar, and I'll just write those down. All right, so this is going to be x minus 3 equals lambda times x, right? Is lambda times x the, let's see, divide both sides by 2, lambda x. And so now I'm going to get x minus lambda x equals 3. Factor out of x. So I get x is equal to 3 over 1 minus lambda. All right. And so that's x. X, this right here, means that x is equal to 3 over 1 minus lambda. And then you would solve for y and z the same way. Okay? And so this right here tells us that y is equal to, let's see, what is y? Y is 1 over 1 minus lambda. This is z is equal to, what is z? Negative 1 over 1 minus lambda. So there's your x, y, and z. So what I'm going to do now is I'm going to take each of these and plug them in to this. So that's going to be 3 over 1 minus lambda squared plus 1 over 1 minus lambda squared plus negative 1 over 1 minus lambda squared equals 4. Okay, so this is going to give me 9 over 1 minus lambda squared plus 1 over 1 minus lambda squared plus 1 over 1 minus lambda squared equals 4. And so this is going to give me 11 over 1 minus lambda squared equals 4. And so this is going to tell me that 1 minus lambda squared is equal to 11 over 4. See, this just goes up there and the 4 comes down into the denominator. All right. So this tells me that 1 minus lambda is equal to plus or minus square root of 11 over 2. And so that's going to give me lambda. Move the lambda over here, this over here. That's going to be 1 plus or minus square root of 11 over 2. So that's lambda. And so from this, I can get x, y, and z. So let me see. Well, I've had trouble grabbing that stuff, and Let's see, what can we do here? I'm going to just write down, I'm going to write down this one and plug it in and show you. So we've got 2 times x minus 3 equals lambda times 2x equals lambda times 2x. All right. So let's take this and solve it. And actually, let's just write it without the 2. We can divide both sides by 2. Okay, we'll get the same thing. All right, so let's plug this in. So I've got x minus 3 equals lambda, which is 1 plus or minus square root of 11 over 2 times x. All right. And so this is going to give me x minus 3 equals x plus or minus square root of 11 over 2x. And so that's going to be x minus x plus or minus square root of 11 over 2x equals 3. See how that goes out? And so I'm left with plus or minus square root of 11 over 2x equal 3. Well, that's going to give me x is equal to plus or minus 6 over square root of 11. All right. So there's x. And so you would do that. You would do that to get y and to get z. Okay. All right. So let's erase this so I can come back up here. So I get x is equal to plus or minus 6 over square root of 11. All right. And so when I do the same thing, plug lambda into this, plug lambda into this, I'm going to get y is equal to, let's see, what is y? Y is plus or minus 2 over square root of 11. And I get z is equal to plus or minus 2 over square root of 11. Okay, so that's what I get. So let's look at this. We've got f of x, y, z is equal to x minus 3 squared plus y minus 1 squared plus z plus 1. Whoop. Plus z plus 1 squared. Okay, so all I did is I just wrote my function down. That's all I did. And what do I have here? Well, I have the point 6 over square root of 11, 2 over square root of 11, and 2 over square root of 11. And then I have the point negative 6 over square root of 11, negative 2 over square root of 11, and negative 2 over square root of 11. That's the 2 points I'm looking at. And actually, I wrote this backwards. This would be plus, and this one would be minus. Okay. All right. So, let's take a look at this. I've got to figure out which one's the shortest distance and which one's the farthest. Okay, which point is closest to that point and which one's farthest from that point. All right. So just look at it. I mean, you would have to take each one of those, plug them in. But basically, we want to see which one's what's going to give us the smallest value, which one's going to give us the largest. Well, look at this. If I take this number and this number and this number. So if I plug this number into here, do you see how I have x minus 3? So I'm going to be taking this much away. Okay? I'm going to get negative 2 point something, I guess. And then plug this one into there. See, I'm subtracting the 1. I'm finding a difference here. And same thing with this one. I'll plug that in for z. I'm finding a difference. So these numbers here are going to be smaller, and they're going to be positive because I'm squaring, and when I square them, the numbers are they're gonna be a little bit smaller. But notice how this one, when I plug this in, it's negative minus 3. So I'm really adding those two numbers together, but with a negative sign in front. But then I'm squaring it, so it's going to make it positive. So you can see how this, and this, when I plug this in, I'm adding. When I plug those in, each of these are going to be larger after I square them. So it's obvious that this is going to give me the smaller value, and this one's going to give me the largest. So this would be the shortest distance, and this would be the farthest. Okay, and that's what they were asking you to find. All right, so that's not too bad. All right, so let's look at this one. It says find the extreme values of f of xy equal x squared plus 2y squared on the disk. D is the set of all points xy such that x squared plus y squared is less than or equal to 1. So if you look at this, we have our disk here. We're not looking at it to where it's just on the outside. We're looking at the entire surface here. You see that? Because it's where it's less than or equal to 1. So we would need to find the maximum and minimum values for on the circle. Okay? On the circle, and then we would need to look in here. Okay? Well, what's nice about this problem, now remember, we want to look where it's on the circle, so that would be x squared plus y squared equals 1. Well, if you remember, we did that problem right here. Okay? So to work the problem we're fixing to work, you would need to do all of this. Okay? You would need to do all of this. So let me write all of this down. So basically what I need is this result here. Okay? You would do all this work and you would get this result. We've already done it in the first problem. So let's write that down here. All right, so let me see. We've got f of 0 plus or minus 1 is equal to 2, and we have f of plus or minus 1, 0 equals 1. So what we need to do now is look for a max or minimum value on this, on that surface inside that circle. That's what we're looking for now. Well, do you remember how to do that? Okay, we're looking for a max min value on the surface that's above that circle. Okay, well that goes back to what we did in the last section. So we have f of xy is equal to x squared plus 2y squared. All right, and so I've got the partial with respect to x is 2x, and the partial with respect to y is 4y. And so remember, we've got 2x equals 0, we've got 4y equals 0, so x equals 0, y equals 0. So we have a critical point at the point 0, 0. Okay, and so now let's evaluate f of 0, 0. So if I take the 0, 0, plug it into here, that's going to give me a 0. So now you can see that f of 0 plus or minus 1 equals 2 is a maximum. And then for this case, f of 0, 0 equals 0 is a minimum. Okay, so this isn't a minimum. It was when we were on the circle out here, but when we look at on the circle all the way into here, it's not. Okay, So that's what they're wanting you to do there. So you would need to do what we did in the first example plus what I just did here, and that would give you the max and min, the extreme values. And it's because it says less than or equal to there. All right. We got one more example to work and we will be done. A method of Lagrange multipliers for two constraints. To find the maximum and minimum values of f of x, y, z subject to the constraints g of x, y, z equals k and h of x, y, z equals some constant c, assuming that these extreme values exist and the gradient g is not equal to 0, gradient of h is not equal to 0, and the gradient of g is not parallel to the gradient of h. So it says, find all values of x, y, z, lambda, and mu such that gradient of f is equal to lambda times gradient of g plus mu times gradient of h. So we're just using a different letter. We're using mu instead of lambda there. We've got two functions there. And it says g of x, y, z equals k and h of x, y, z equals c. The numbers lambda and mu are called Lagrange multipliers. All right, so it says evaluate f at the points x, y, z that result from step 1. The largest of these values is the maximum of f, and the smallest is the minimum value of f. So basically, we're working it the same way that we did last time. We just have two constraints. All right. So it says find the maximum value of the function f of x, y, z equals x plus 2y plus 3z on the curve of intersection of the plane x minus y plus z equals 1 and the cylinder x squared plus y squared equals 1. All right, so let's just go ahead real quick and let's just write down our functions here. Equals x plus 2y plus 3z. And we've got g of x, y, z equals x minus y plus z equals 1. And then we have h of x, y, z equals x squared plus y squared, and that is equal to 1. All right. So we've got all right, so there we go. Just writing out like we did last time. It's just we've got two constraints this time. That's all. All right. So this is the partial x, and that's going to be lambda partial of g with respect to x plus mu partial h with respect to x. Okay, we just got an extra term in there. That's all. And then we've got fy is lambda gy plus mu hy, and then partial f with respect to z is lambda partial g with respect to z plus mu partial h with respect to z. Okay. All right. And then of course you have, you got your two constraints there. I'll write them down later. All right, so let's see what we have here. So the partial of f with respect to x is 1. And then the partial of g with respect to x, that's 1 also. So that's just going to be lambda, right? Partial of g with respect to x is 1. So 1 times lambda is lambda. Plus, then the partial of h with respect to x, that's going to be 2x times mu. And then the partial of f with respect to y, that's going to be 2 equals, what is that? Negative lambda plus 2y times mu. Okay, partial of this with respect to y is 2y times the mu. And then partial of f with respect to z is going to be 3 equals lambda. And that's it, because this doesn't have a z term, so that's just 0, so we get lambda equals 3 there. And then, of course, we have, let's see, where do I want to write those? Let's write it right here. I've got x minus y plus z equals 1, and I've got x squared plus y squared equals 1. So there's my equations. I've got to solve that, don't I? Okay. All right, so now let's take, let's see, how do we want to do this? What would be the easiest way? Well, I know lambda is 3, so if I plug 3 in for lambda, that's going to give me 1 plus, that's going to give me 1 equals 3 plus 2x mu. And so, let's see, what does that give me? That's going to give me, that's going to be negative 2, negative 1 equals 2x mu. So I get x is equal to negative 1 over mu, right? And then if I plug the 3 in for lambda here to solve for y, that's going to be 2 equals negative 3 plus 2y mu. And so 5 equals 2y mu. And so I get y is equal to 5 over 2 times mu. All right, so what can I do there? Well, this would what? This is going to allow me to solve for mu, right? I can take this and plug it into here. So that's going to give me negative 1 over mu squared plus 5 over 2 mu squared equals 1. So that's 1 over mu squared plus 25 over 4 mu squared equals 1. So if I get a common denominator here, that's going to give me 4 over 4 mu squared when I get the common denominator. So that's 29 over 4 mu squared equals 1. And so that's going to tell me that mu squared is equal to 29 over 4. So I get mu is equal to plus or minus square root of 29 over 2. All right. So there's mu. So what can I do here? Well, let's well, I've got mu. Okay, so I can take this and plug it into here and get x and y, right? All right, so let's do that. So x is equal to negative 1 over plus or minus square root of 29 over 2, which means that x, or which implies x is equal to plus or minus 2 over square root of 29. All right. And then I've got y is equal to 5 over 2 times plus or minus square root of 29 over 2. And hang on just a second. I'm going to have to, I made a mistake over there, up there with the x. I'll fix it in just a minute. So this is going to mean that y is equal to 5 over, well, plus or minus 5 over square root of 29. That's y. All right. Now, this is where I messed up. Right here. So notice how this is plus or minus, but this is a negative right here. So that negative and positive is going to be a negative, and the negative and negative is going to be a positive. So those signs are going to flip. Okay. All right. So we've got x, we've got y. Okay. And so what do we need now? Well, now we need z. So for z, let's see, let me find everything here. Oh, here we go. So you see this, I can solve that for z. So I get z is 1 minus x plus y. So z is equal to 1 minus x plus y. And so that's going to be z is equal to 1 minus negative minus or plus 2 over square root of 29 plus, and that's going to be plus or minus 5 over square root of 29. And when you do all that, I mean, you can do 1 minus negative 2 over square root of 29 plus 5 over square root of 29, and then 1 minus positive 2 over square root of 29 plus minus 5 over square root of 20. You can do them separate. And when you do all that, you're going to end up with 1 plus or minus 7 over square root of 29. That's z. Okay. And so now what we want to do is evaluate our function at the point. So our point is what? Negative positive 2 over square root of 29. Square root of 29 plus or minus 5 over square root of 29. And then 1 plus or minus 7 over square root of 29. So that's what we're evaluating the function at. So that's negative positive 2 over square root of 29 plus or minus 5 over square root of 29, and then 1 plus or minus 7 over square root of 29. And so let's see, I need to write my function down again. I think it is x plus 2y plus 3z is our function. Yeah, x plus 2y plus 3z, that's our function. And so I'm going to take this and plug it into here. And so that's going to be negative positive 2 over square root of 29 plus 2 times plus or minus 5 over square root of 29 plus 3 times 1 minus plus or minus 7. Yeah, 1 plus or minus 7 over square root of 29. And like I said, you can do the minus plus plus, you can do that, and then you can do the plus minus minus. You can do them all separate if you want. But what you're going to end up with there is 3 plus or minus square root of 29. And they want us to find the maximum value of the function subject to those two constraints. And so you can see that 3 plus square root of 29 is larger than 3 minus square root of 29 is the maximum value of f on the given curve. And there's your answer. All right. So, I mean, you know, just a bunch of arithmetic and algebra is all it is. It's not bad. All right. So, and yeah, you know, some of them can get complicated, can get pretty nasty, but it's all good. All right. So I hope you enjoyed that video. I hope it helped. Check out my other videos. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.